So this lesson is going to introduce us to exponential functions. It's the first lesson in this unit on exponential and logarithmic functions. So let's make a connection first with the activity we did before this, where we asked the question, how many dominoes would it take to topple a skyscraper? Now, you already worked through that problem, and we found that it was around 28 or 29. If we started with the first domino being only 5 millimeters tall, but each one was 1.5 times larger. So let me try and represent what that would actually look like on the screen here. So if you look at the bottom left corner of the screen, you're going to see some little dots appear. These are our dominoes, starting with 5 millimeters. And if you can see, the first 7 or 8 dominoes, they all look the same because I can only make the dot so small on the screen, but now they slightly start to increase in size. And then as we get a little further out, we start to see a very rapid growth, right, in the height of our domino till we get to about the 29th domino. Now, if we were to try and fit a curve through the top of each of those dominoes, it would look like this. Right? It would start out looking kind of flat, but then get steeper and steeper and curve up as we get to the larger dominoes. So this is a perfect example of exponential growth. The growth in the height of the dominoes is exponential. And we'll see in a minute, we get exponential growth when we are multiplying the previous value by a value greater than 1.5 in this case. All right, let's look at our objectives for this lesson. So we're going to be able to identify whether an exponential function is growth or decay, right? We've talked about growth so far, but it could also be decaying, meaning getting smaller. We'll see what does it look like if we graph an exponential function using a table of x and y values. So let's look at a couple more examples here beyond the dominoes. Population growth of tree frogs. So tree frogs, not here in California, but you get down into the tropical areas and they're quite common. They're quite colorful. Their color protects them. I guess I should say the color attracts predators, but most of them are poisonous, so they know to stay away from them. All right, so let's pretend in week 0, we had 2 tree frogs, okay? Now, assuming you need both the male and female, that's the minimum we would need to start. And then it says the population doubles every week. So we'd have 2 frogs the first week, the second week, right? That's going to double to 4 frogs. The first week after our starting point doubles to 4 frogs. The second week, right, we'd be up to 8. And the third week, we would be up to 16. Okay, so this is an example of exponential growth. Here we're multiplying by 2 each time. So we could fit a curve to that and it would have that nice, smooth, characteristic shape of exponential growth. Now, the form we're going to use for describing an exponential function looks like this: y equals a times b to the x. So y represents the total population of the tree frog. B is going to be our growth factor. Okay, so if it doubles, right, we would put a value of 2 in there. X is the number of time periods in this example. Okay, so week 1, week 2, week 3, those would be the values we put in for X. And A is our starting population, our starting value. Okay, so in this example, right, we started with 2 frogs. So let's put all those values in here. If we were to write an exponential function that models the growth of tree frogs, it would look like this: y equals 2 times 2 to the x. So notice our variable x is always going to be in the exponent. It's not 2 times x, it's 2 raised to the x power. That's what makes it an exponential function. If we wanted to create some more values here beyond week 3, we could do it in a table, right? And so if we put in 0 for x, remember, anything raised to the 0 power is 1. So we'd have 2 times 1 gives us 2. Same as what we did on our graph. Week 1, 2 to the first power is 2. So that would give us 4. Week 2, 2 to the second power gives us 4 times 2 is 8, and so on. Right? So we know how to simplify this. So in the fourth week, 2 to the fourth is 16 times 2 is 32. Let's look at another example, bacteria growth. Okay, so here it says bacteria triple their population every day, and the starting population is 1 bacteria. So we want to do 3 things: write an exponential growth function, calculate the population for the first 3 days. We'll actually fill in a table for the first 5 days here, and then sketch a graph of the bacteria growth. All right, so here's our starting function, right? What value are we going to put in for A? Remember, A is our starting value, so that's going to become 1. X is the number of days, and B is our growth factor. So here it says that it triples every day. So let's put those values in, right? We're going to have 1 for A and 3 as our growth factor. We still always will have X in the exponent as we write this as a function. So Y equals 1 times 3 to the X. That's our population. So let's put some values in. If we put in 0 for X, we know we get 1. 1 times 1 is 1. We put in 1 for X. 3 to the first is 3 times 1 is 3. 3 squared is 2. 3 cubed is 27. 3 to the fourth power is 81. And 3 to the fifth power is 243, right? We're multiplying by 3 each time. All right, let's look and see what the graph might look like. Now notice we're going to use a different scale on the x-axis than what we do on the y-axis, because we have much larger values on the y-axis than we do the x-axis. Okay, but we still want to pick a scale on the y-axis that will allow us to plot these larger numbers. And you're going to be doing an assignment in this lesson here at the end, where you're going to have to create your own data and create your own graph or sketch your own graph. So it's very important you pick a scale on the y-axis that you can fit your values in, and then plot them according to that scale. We don't just take the 1, 3, 9, 27 and spread them out evenly on the y-axis. All right, let's put those points in. So 0, 1 would be right there. 1, 3 would be there. 2, 9. 3, 27. 4, 81. And 5, 243 would actually be off the graph a little bit, right? Our graph went up to 200 here. So we can fit a nice smooth exponential curve to that. And that's what the graph would look like. All right, let's look at one more example here. This time we have population decay. So decay is similar, except instead of the values growing exponentially, they're going to be shrinking or becoming smaller exponentially. So what's our example here? Each round, 1/2 of the players are knocked out of the tennis tournament. The starting number of players is 128. So we want to do the same thing, write an exponential function, this time for decay, calculate the number of players after 4 rounds, and then sketch a graph. All right, so here's our form, y equals a times b to the x. Starting number of players, well, we're given that, 128. X will be representing the number of rounds, and B is the decay factor. So it says each round, 1/2 of the players are knocked out. So we're going to multiply by 1/2 or 0.5 each time. And then Y will give us the number of players left in the tennis tournament. So here's our function, Y equals 128, our starting value, times 0.5 raised to the x power. So if we plug in a 0, right, 0.5 to the 0 power is just 1, so that leaves us with 128. If we plug in 1, we get 0.5, so half of 128 is 64. We're basically going to keep taking half of that value each time. So 64 becomes 32, 32 becomes 16, 4 becomes 8. So at the end of 4 rounds, we would be down to 8 players. All right, let's see what the graph would. I'll leave the graph for you to sketch here, but it would be similar to what we did in the other examples. All right, so let's officially define here what an exponential function is now that we've looked at a couple examples. The general form is y equals a times b to the x. But some conditions we have to apply here. A could not be equal to 0, right? That would say if our starting value is equal to 0, we're never going to see exponential growth. B has to be greater than 0. It cannot be negative, but it can be a fraction, less than 1, right? And then B cannot be 1. If it grows by a factor of 1, then there is no growth, right? We keep multiplying by 1 and it won't change anything. So as we simplify this, remember the exponent x only applies to our growth factor b. Then we multiply by a. Now, here's the criteria for whether it's growth or decay, right? By looking at the function, we should be able to determine that. So if b is greater than 1, like we saw in the first two examples, right? For the frogs, it was a factor of 2. For the bacteria, it was a growth factor of 3. If b is greater than 1, then it's going to be an example of exponential growth. So the curve would look something like that. If b is less than 1, but greater than 0, so it's a fraction, it's going to represent exponential decay. So the values will continue to get smaller and smaller. So the graph would look something like this. There's an example of decay. As we go out to more positive values of x, we get smaller values of y. Okay, so here's the general form that we'll be using. All right, so let's just see if we can determine whether these functions are growth or decay. So remember, all we're going to look for is the b value. And if it's greater than 1, it's growth. If it's less than 1, it's decay. All right, 1/2 times 2 to the x power. So a is a half, right? B is 2. So since b is greater than 1, this would be growth. It would look like this if we graphed it. All right, how about you do this next one? Just pause it here and figure it out. This time b is less than 1, 0.5, so this will be decay. All right, let's try a couple more. A is 4, our starting value. Our growth factor is actually 1/2, so it's a decay factor. Another decay example. Here's D. See if you can figure this one out. So our starting value is 0.8, but all we really care about is the B value. So 8/7, that is greater than 1. This is going to be growth. All right, a couple more. And the last one. All right, so that's really the key concept for this lesson. We're understanding what the general form is for an exponential function and how to determine whether or not it's growth or decay. It all has to do with the b value that we're raising to the x power. All right, so let me talk a little bit about the assignment that's going to go with this lesson. Okay, I don't have a set of problems for you to do, but what you're going to be doing is defining a model for zombie, and you don't have to do zombies. You can do any living thing that you choose. I guess it doesn't even have to be living because zombies technically are not living things. But define a model for some type of growth or decay. Okay, and when I say define a model, I want you to write a complete sentence, right? You would say something like, zombies start with a population of 100 and it doubles each week, right? That would be an example of a complete sentence. So you're going to start by picking a population for your zombie at the beginning, right? So what I just said was 100. That would be an example of our starting population. and pick a growth or decay factor. You can do either one. They're either growing or decreasing. So you could say something like they double each year, or they are reduced by 1/2 or 0.5 each week. Then I want you to write your exponential equation in the form of y equals a times b to the x. But what are your a and b values? Then create a data table for the values out to 8 time periods. Okay, so that would be kind of 0 is your first time period, and you would go out to a value of x to at least 7. Then I want you to graph your data, and you need to be careful with this. You could use graphing tools online to do this, or you can do your own graph on a piece of paper, but I am going to be looking for correct scaling of both your x and y axes, so that when you plot your data, you get a nice exponential curve. So you're going to do all of this on a piece of paper. You could do a larger piece of paper if you want, and then take a photo and post it in Google Classroom. Or you can do this in a Google Doc or a Google slide, right? And create the different elements in it, and then submit that. And then I want you to have a little fun with this, right? Do some type of drawing, or find some images that you can add to it that show the object that you're doing. So zombies or whatever else you choose, and make it colorful, right? Add a little artistic flair to it. Okay, so that's what you're going to create as the assignment for this lesson. Now, here's kind of the rubric for it, right? What am I going to be looking for? The sentence which describes the population with the starting value and growth or decay factor. The function that you're going to write, y equals ax plus b, or I'm sorry, y equals ab to the x power, excuse me. And then the table of x and y values. And then the graph, of course, with proper scale and both axes labeled. And then I'll be looking for kind of how much artistic embellishment or additions, right, that will earn you some extra points here. Okay, so that's it for the lesson and the assignment. I will be posting these last 2 slides here as the lesson assignment separately also in Google Classroom.